All right, welcome back. This is episode 5 in our AP review series, and today we're going to look at what I'm going to call derivative applications, part 1. And part 1 is going to include both particle motion, derivative side of particle motion, and then related rates. So let's start off with a little bit of talk about particle motion. Just a quick conceptual overview of some things you should know on the derivative side of this, and then a quick example or two. So some things that we should know. First, let's talk about position. Position represented by x of t or s of t represents a location. Could be thought of as distance or height or something along those lines. A location at some time t. Velocity represented as v of t, the derivative of position. Tells you how fast something is going and in what direction, positive direction or negative direction. That could be right, left, up, and down, depending on the problem. And then acceleration, call that a of t, is the first derivative of velocity, and it is the second derivative of position, which tells you the rate of change in the velocity, how fast the velocity is changing at any time t. Whereas velocity is how fast the position is changing. Remember that the speed of a particle is the absolute value of the velocity. Get rid of the direction, just how fast is it going. Remember that when velocity and acceleration have the same sign, the particle is speeding up. They're working together. You throw, you drop a ball from a cliff, and the velocity is acting in the downward negative direction, and the acceleration due to gravity is also negative. It's getting faster. Remember, when they are opposite signs, the particle is slowing down. Pretty easy to work with this, and I would be ready to work with this both algebraically and graphically. So if a problem were to give you an equation for position, you should be able to easily take the derivative and get velocity 2t minus 4. Acceleration would just be 2 in this case. You should be able to tell me when is the particle at rest. This would be when velocity equals 0. So that's going to happen at time 2, right? And at that point, you can even determine, does it change direction by making a quick sign change chart. If I put a 2 right here and pick a point, maybe 1, and plug that into my velocity, we can see it's negative. If I pick a point over here, maybe 3, and I plug it into velocity, and positive. So it's traveling to the left. Anywhere velocity is negative, it's traveling to the left. Anywhere velocity is positive, it's traveling to the right. We're in the positive direction. You could tell me, let's say at t equals 3, is speed increasing? Well, let's look at both velocity at time 3, which we just said a second ago was positive, and acceleration at time 3. Acceleration in this problem is always positive. So the answer would be yes, because they are the same sign. If they were both negative, it would be yes. If they were different, then it would be a no, speed would be decreasing. If acceleration was 0, equal to 0, the particle will be moving at a constant rate. Now, you should also feel very, very comfortable graphically working with this. In this video, I'm going to just throw up a quick velocity graph, right? Maybe your velocity of your particle is modeled by this graph right here. We'll put this over here where it belongs. So my vertical axis is representing the velocity. My horizontal axis is representing time. And we should be able to look at this and say, several things. And let's say that this time here is 1, 2, 3, 4, and 5, and then 6. So from time 0 to time 4, we can see that the particle is traveling to the right. And we'll talk about area in a later lesson. We can see at time 4, the particle changes direction. It stops and switches to the negative direction. It's traveling to the left from time 4 to time 6. So it moves this way and then back some this direction. We can see acceleration on the velocity graph as the slope, right? The slope here, we have a positive acceleration with a positive velocity. The particle is getting faster. We have a zero acceleration up top because the slope is zero. So we're moving at a constant rate. Here, the acceleration is negative because the slope is negative. So there, we're slowing back down because the velocity is positive and the acceleration is negative. But when I turn around, now they're both negative, so we're getting faster. And then we, again, here, the acceleration goes back to a positive, so we're slowing back down, and then we're at rest again at that point, right there. So I'd be very comfortable with the velocity graph and how to interpret some different things. And we'll talk about interpreting location with integration in a later lesson when we get to that point. Okay, that's all for now with particle motion. Let's take a look at related rates. And I'm a big fan of related rates. It's one of my favorite topics in differential calculus. And remember, related rates, it gives you some situation, right? So imagine you have some scenario where multiple things are changing in that problem. The classic example that everybody always probably starts with is the sliding ladder problem. So if my ladder is leaning up against a building, forms a right triangle right here. Let's say that I'm standing on it, and unfortunately that ladder begins to slide down this wall. So as the ladder is sliding down the wall, the base of the ladder is sliding away from the wall this way. So this vertical side is getting smaller, and this horizontal side is getting larger. So we have several rates of change here. There's only two rates of change. The change in the ladder is zero because that's constant, it's not moving. But we are decreasing here, we are increasing here. Don't focus on the direction, focus on whether it's getting larger or smaller when we talk about positive rates or negative rates. Now, the rule with related rates is your job is to come up with a formula that relates the picture. What is the equation that relates this? The sliding ladder problem is the Pythagorean theorem. Maybe the problem throws an angle of elevation. Now have one trick. Some type of formula relates that problem. Your job is to take the derivative of that formula and then plug in everything the problem gives you and solve for whatever is missing. The problem sometimes will give you a constant, like in this case, the ladder. Constants are the only thing that can be plugged in before taking the derivative. So if you recognize a constant in the problem, feel free to plug that in pre-derivative. And I'm going to do an example that we can actually see both doing that at the beginning or doing that at the end. You'll see how it doesn't really matter. But let's do a problem. So let's do a quick example. I'm going to tell you a cylindrical tank is losing water at a rate of 5 cubic feet per minute. And I'm totally making this problem up right now. I hope it works out okay. At what rate is the height changing when the height of the water is 4 feet? And I also need to tell you the size of the tank. Would maybe, let's say, have a radius of 3 feet and a height of 10 feet. Okay, we got a lot to break down. We have a cylindrical tank. Maybe the problem gives you a picture, maybe it doesn't. So I'm going to draw one to go with this. So here's my cylindrical tank. We know that the radius of the tank is 3 feet. And we know that the height of the tank is 10 feet. And this tank has some water in it, right? And we are highlighting the point when the height of the water is 4 feet. So every related rates problem is going to sort of pause the problem at some instant. They ask you to solve for some rate of change in that instant right there. So when I think about this problem and I analyze what I'm given a rate of change in the amount in the water being lost. So I'm going to call that rate of change dV dt. And it's going to be a -5 because it's getting smaller. They want to know dH dt, at what rate is the height changing. And then in this problem, dr dt is a 0 because it's constant. This cylindrical tank, its radius is not changing. Don't assume every cylinder problem has a dr dt equal to 0. There have been problems that have messed with you on that part. So just be prepared to really break down what's going on in the question. All right, and then the formula. What is the formula that relates this picture? It is the volume of the cylinder, pi r squared h. A lot of times that's given to you in the problem. Okay, so from here, things that I can do. Before I take the derivative of this, because r is constant, I can substitute in the radius of the tank, 3 feet. So I could plug in 3 for r and get an equation of 9 pi h, and then take the derivative. dV dt equals 9 pi times dH dt. And then from there, I can substitute in what I know. I know that dV dt is -5, and dH dt is what I'm solving for. So then I can just divide and say that dH dt is -5 over 9 pi feet per minute. And I'm done. And that works great. It's a really easy way to do that problem. So the question would be, what if I didn't, at first, maybe I didn't realize the radius was constant. What do I do then? Well, let's solve the problem that way. So this time, when I take the derivative of pi r squared h, as it is, I'm going to have to use the product rule. So we're going to have pi r squared times dH dt plus h times 2 pi r dr dt. And we'll notice, look at what happens here. Now, hopefully you realize, what's our dr dt? Oh, it's not changing, right? So all of this stuff, when I plug in 0 for dr dt, is going to go away. And then if you look at my equation that's still left, it is the same as the equation that we had up here once I plug in the radius. So either way is going to get you the same answer. This way I've done here in purple is just going to take a little bit more work to get there. It's a much harder derivative to take in that problem. Remember, you're always deriving your variables implicitly because you're taking the derivative of each one in terms of time. And then plug in what you know and solve for whatever's missing. Don't overthink related rates. Focus on the formula, what you know, take the derivative, and then plug in and solve the problem. Okay, that's it for today with the derivative applications. We'll do more next time, and happy studying.